Welcome back to part 2 of our conversation about vector operations. In the last lesson, which did not have a video, you did some independent work learning how to add and subtract vectors and multiply vectors by a scalar value. Today, we're going to build on those skills by working more with unit vectors and finding the angle between two vectors. Before we get into more advanced vector operations, I want you to ponder how you might answer the question shown here. Find a vector v that has a magnitude of 5 and has the same direction as -7, -3. Use your guided notes and try answering this question on your own. Include any ideas you have about the steps you'd take to tackle this problem or any questions you have about it. How did that go? It's okay if you got stuck or felt like that was a lot of steps. We'll revisit that question again in a bit, after we spend a little more time with unit vectors. You'll recall from our previous lesson that a unit vector is any vector whose length or magnitude is 1. A unit vector's job is to specify direction. Since vectors are defined by both their length and direction, we can simplify vector operations by setting the vector's magnitude to a length of 1, allowing us to focus purely on its direction. Let's see how to do that. Our instructions are to find a unit vector in the direction of v. What is this asking us to do? We can restate it like this. Find a vector in the same direction as v, but with a length of 1. To do that, start by identifying the component form of v, which would be 3, -4. What is the magnitude of v? Yes, the magnitude is 5. We need to shrink v and create a new vector, u, in the same direction, but with a magnitude of 1. How might we do that? This concept makes me think of similar triangles. What scaling would we need in order to change this 3, 4, 5 triangle so that its hypotenuse measures 1? Right! We need to scale the whole triangle down by a factor of 5. That means we need to multiply each component by 1/5, so the horizontal leg, which corresponds to our horizontal component, will be 1/5 as long, or 3/5. The vertical leg will also be 1/5 as long, so the vertical component is -4/5. Our new unit vector will have the component form 3/5, -4/5. Before moving on, I encourage you to use your guided notes to verify for yourself that the magnitude of vector u is indeed 1. Before you try one on your own, let's summarize our steps. We started with the component form of vector v. Then, to find the unit vector u, we divided each component by the magnitude of v. We can generalize the process with this formula. If v is a non-zero vector, then vector v divided by the magnitude of v gives a unit vector in the same direction as v. Now you try it. Find a unit vector in direction of w and write your answer in ai plus bj form. If you end up with any radicals, it's okay to leave them in the denominator and not rationalize the denominators. How did you do? W's component form is -7, -3, and it has a magnitude of √58. We divide each component by the magnitude, which means that the component form of the unit vector is -7 over the square root of 58, -3 over the square root of 58. And in ai plus bj form, we get u equals -7 over √58i minus 3 over √58j. Remember how I said that unit vectors can help simplify other vector operations? Let's revisit the question I asked you at the beginning of the video. Find a vector v that has a magnitude of 5 and has the same direction as -7, -3. Let's see how unit vectors can help make this problem much easier. We just worked with a vector that has the component form -7, -3, didn't we? We found that its corresponding unit vector is -7 over the square root of 58, -3 over the square root of 58. That unit vector has the same direction as -7, -3, but it has a magnitude of 1. Can we scale the unit vector's magnitude from a length of 1 to a length of 5? Yes, we did that in the last lesson. Do you remember what to do? We simply need to multiply each component by 5 to get a vector v with components -35 over the square root of 58, -15 over the square root of 58. What else can we do with vectors? You have added and subtracted two vectors, multiplied vectors by a scalar, and, as we just saw, divided vectors by their magnitude to produce a new unit vector. Do you think it's possible to multiply two vectors together? Since vectors are defined by two values, their magnitude and their direction, we can kind of think of them as having two dimensions, just as rectangles have both length and width. But when it comes to multiplication, would it make sense to multiply two rectangles together? It doesn't really make sense, does it? Vectors are complex mathematical quantities that help us describe phenomena like projectile motion, electrical currents, the laws of motion in the physical world, and so much more. And we're barely scratching the surface of their properties in this course. Further work with vectors shows us that there are two different ways to multiply vectors. One method is called the cross product, and it is used for multiplying vectors in 3 dimensions. The cross product, which is notated with this x, results in a new vector in a 3rd dimension. We won't cover the cross product in this course, but let's take a look at the other method for multiplying vectors. The other method of multiplying vectors is called the dot product. The dot product results in a scalar value and can be used with vectors in any dimension, but it's especially useful for working with vectors in more than 3 dimensions. Let's learn how to find the dot product of two two-dimensional vectors. Start with vector A, denoted a sub 1, a sub 2. And vector B, denoted b sub 1, b sub 2. Vector A dot vector B is found by multiplying the horizontal components, multiplying the vertical components, and adding the results together. The result will be a number, a scalar value, which we'll call C. Before we give it a try, take note that the dot product's notation is, well, a dot. Remember to use the correct symbol. Let's give it a try. In your guided notes, find the dot product of vector u and vector v. How did you do? Begin by multiplying the horizontal components. -8 times 1 is -8. Then the vertical components. 2 times 6 is 12. Add the results to get 4, which is the dot product of u and v. Now let's look at how the dot product is used in our final vector operation for today. Many of the uses for the dot product are, again, beyond the scope of this course, but one way we will use the dot product is when we are finding the angle between two vectors. Let's wrap up today by learning how to do that. Before we find the angle between two vectors, begin by recalling something you learned at the beginning of this unit. the law of cosines. The law of cosines allows us to find one angle of a triangle when the three sides are known. If we shift our thinking just a bit, we can visualize this triangle in a slightly different way. As two vectors, A and B, and their included angle theta. The law of cosines is used to derive a formula that finds this angle theta between the two vectors. The cosine of theta is equal to the dot product of the two vectors divided by the product of their magnitudes. If you'd like to see the full derivation of this formula, you can find that in your lesson materials. This formula will help us with our final task for today. Find the angle in degrees between vector A and vector B. These two vectors have component form 3, 2, and -1, 4. Since you know how to find the dot product and magnitude of vectors, try using this formula to find the angle on your own. How did you do? Let's walk through it together. First, I found the magnitude of each vector. The magnitude of A is square root of 13, and the magnitude of B is square root of 17. I also know that I'll need to find the dot product of A and B, which will be the sum of 3 times -1 and 2 times 4. The denominator will be the product of the magnitudes, or square root 13 times square root 17. Simplifying this gives me 5 over the square root of 221. Using the inverse cosine function on my calculator gives me a measure for theta of 70.3 degrees. Is that what you got? If your angle is slightly different than mine, it might be because you rounded more than once or too early in the process. Try inputting cosine inverse of 5 over the square root of 221 into your calculator or GeoGebra as a single step, and be sure your result is 70.346. Great work! Let's review our key takeaways and formulas from this lesson. First, to find a unit vector in the same direction as vector v, we can divide each component by the magnitude of v. Second, we learned that one way to multiply vectors is with a specific operation called the dot product. Finally, we used a formula derived from the law of cosines, which also involves the dot product, to find the angle between two vectors. Be sure to finish all of the guided notes in your lesson materials and review the lesson activities before completing the online practice. In the next lesson, we'll see just a few of the many ways that vectors are used in real-life applications. See you then! Hey, hey.